welcome to Introduction to Composites. Today is the start of the second last week of this course, and what we plan to do over this week and also the next week is try to develop a method through which we can predict the stiffness of laminates, not just individual lamina, but entire laminates which are stacked up sequences of different layers of unidirectional composites, and then also figure out how to predict failure in these laminates. So, till so far in this course what we have learnt is that the first thing we learned was how to predict stiffness of lamina. This is what we learnt, and specifically in that too we learnt when it was a unidirectional lamina and the orientation of the load and material axis, they were aligned. So, this was the first theme of this course, and we were able to predict the stiffness of the lamina and also the strength of the lamina. And then as a next step, and this first step we did, we expressed stiffness of the lamina in terms of first material constituents, which are fiber properties and matrix properties, and then once we were confident of predicting the stiffness of lamina when the load and material axis both are aligned, then we made it a little more general. So, we in the next step we still focused on a lamina, but then our situation was that load and material axis not necessarily aligned. So, this is what we learned over last couple of weeks, and so we are at this stage, and once we did that, we also evaluated how to predict failure in such situations. Okay. So, these are the two broad things we have learnt. So, the next step is that stiffness and failure of laminates. Of laminates. This is what we will focus on. So, what is a laminate? It is a series of lamina, individual layers of composites, and they are all glued together. So, a laminate, if you look at its cross section and you zoom in, then it may have several layers of composites. So, this could be 1, 2, 3, 4, 5, 6, and whatever number of layers could be there, and each layer could be different. It could be different in terms of material properties, and it also could be different in terms of orientation. So, what we will learn is a method to predict the stiffness of a thick laminate, and also later we will learn how to predict failure in such laminates. So, we will make certain assumptions before we start developing this theory. So, we will make some assumptions. So, the first assumption we will make is that each layer, the bond between two layers is of 0 thickness. This is one assumption we will make, that bond between two layers is of 0 thickness. What that means is that total laminate thickness So, this equals sum of thickness of each layer, each lamina. So, we do not have to worry about the thickness of the bond between two layers, that is one thing. The second assumption we will make is bond is perfectly rigid. Perfectly rigid. So, what that means is, so the second assumption as I mentioned is that bond between two adjacent layers is perfectly rigid. Now, that has a very significant implication. So, consider this book, okay, and just assume that each of these pages is an individual layer or a lamina. Okay. Now, if the bond was not rigid, or rather the bond was not existence, if the bond was non-existent, then as I bend this book, right, as I bend this book, one layer slides on top of each layer, the adjacent layer. So, as I bend it, page number 1 slides on page number 2, page number 2 slides on page number 3, and so on and so forth. So, this is how the edge will look like. When it is not bent, the edge is straight. When it is bent, then edge becomes longer, and also each layer slides on top of or below adjacent layers. But when the bond is perfectly rigid, which means when I bend it, there is no sliding, there is no sliding going to happen, and when there is no sliding going to happen, then, so I'll actually draw a picture. So, suppose there is a laminate which has 2 layers only, and if the bond is perfectly rigid, then when it bends, then this edge will remain straight. Okay. So, this is the deformed surface laminate. Suppose I want to bend this laminate, then this edge, it remains straight, and this angle, it also remains at 90 degrees. So, this is when you have perfectly rigid bond. Okay. If the bond was not perfectly rigid and there was sliding which was being permitted, then the shape may not look like this. So, this would have been the ideal shape, but it may look something like this, this angle, this may not be equal to 90 degrees. So, this is when flexible bond is there at interface. Okay. So, this is a very important assumption. Okay. So, a bond is perfectly rigid. Mathematically, it means several things. Perfect rigid bond, it implies a no shear strain between the layers, each lamina. Okay. And if this is my z axis, if this is my x axis, and the plane vertical to the computer screen is y axis, if there is no shear strain between each lamina, essentially what that means is that gamma yz equals gamma xz equals 0. Oh, I am sorry, gamma yz comma equals gamma y, yeah, zx, this is equal to 0. This is another implication. So, first implication is that if the bond is perfectly rigid, it does not permit any shear strain gamma yz or gamma zx. The other thing is, if the bond is perfectly rigid, then the other thing it means is that this angle, so see this angle was theta. So, theta was initially 90 degrees, and when there is bending of the plate, theta still remains 90 degrees. So, this is the normality assumption. So, what in words what we say is that line perpendicular to mid plane. So, this is the line which is this is the mid plane, this is the mid plane, and this is the line which is perpendicular to the mid plane. So, this is line, let us say AB, and once the thing has bent, this is A prime, B prime, our mid plane is this, and the line A prime B prime is this. So, line which was, so which line we are talking about? We are talking about line AB. So, line which was perpendicular to the mid plane originally it was originally, this also remains straight. So, it does not develop any curvature, it remains straight and perpendicular to deformed mid plane. So, this theta still remains 90 degrees, theta still remains 90 degrees. So, this is the second thing. And the third assumption we make is that whenever we have a composite plate, so this is its thickness, and thickness is represented by line AB, and when I put loads on it, suppose I put some external load, the thing may bend and twist and do all sorts of things, but one thing we know that will not happen. So, this is the bend configuration, is that the length of line AB, the length of line AB will not change, because all the external loads are only causing the plate to bend. Nothing is getting the there is no force which is actually compressing the plate from both sides. Okay. So, length of line AB does not change. This is another assumption we make, and essentially mathematically what it means is that epsilon z is equal to 0. So, these are the three assumptions which we make. Okay. And based on these assumptions, now what we will do is we will develop a relation for strains in such a plate. So, we will develop strain displacement relations. In a laminate. So, this is we will develop relations between strains and displacements. So, now what we are going to do is, based on these assumptions, we will develop relations between displacements in the three directions u, v and w and strains, and we have already said that three strains are already 0, epsilon z, gamma yz and gamma zx. So, the three strains we will really worry about are epsilon x, epsilon y and the shear stress I am sorry the shear strain gamma xy. So, what we will do is we will start by drawing a picture. So, So, consider this. So, this is a small flat plate. So, what I will draw is I will also draw the mid plane. So, plate has uniform thickness and the green line represents the mid plane of the thing, and I now draw the coordinate system. So, from the coordinate system, when we go down towards the bottom side of the plate, that is the positive z axis. So, this is the convention we are going to use, and this is the x axis, and the third axis is y axis. So, we have 3 axes x, y and z as depicted here. The x axis runs on the mid plane of the plate in this direction. On the mid plane also we have y axis, and going down is positive z axis. And so, let us look at a small portion of this plate. So, what we are going to see is, so this is a small portion, and in this portion we have this small portion, and let us call this top point as A and the bottom point is D. So, this is a, so I am cutting a small portion and I am looking at it, and then I zoom it, and this is the deformed undeformed position. So, when I look at the undeformed position, it looks like this. So, this is a significantly zoomed view. So, the top point is point A, the lower point is point B, okay. And the mid plane in this view appears as a just a line, because we are looking at it from the end. So, this is my mid plane, and the plane point where this mid plane cuts the edge AB, that is point B. So, this is my x axis, and my, excuse me, this is point D, so the lower point is point D, this is point D, this is point A, this is point B, and the axis going normal to the plane of this board, that is my y axis. And I now identify another point on this line AB or AD, and I will call that. So, this additional point is point C, and this particular point, so this is z axis, vertical axis going down is positive z axis. So, this distance is x, no, z. So, the location of point C is z millimeters down in the z direction, okay, on line AB. So, this is undeformed situation. This is undeformed situation. Now, when I put some load on this composite plate, so I can put some extra mass or weight, then this composite plate is going to bend. So, what I will do is I will draw the bent configuration also. So, these are my original lines. Now, two things can happen. One is I have a plate and I can pull it like this, and as I pull it, this line AD, it will just move horizontally in the x direction. That is one thing which will happen. So, that is a translation, a line AD will move and it will translate, okay. Then, and if I also put some extra loads on top of that, this line AD, which is this vertical line, it will not only move because of the stretching thing, but it will also rotate. It will also rotate. So, both these things can happen because of extensional things, it can stretch and it can also rotate because of vertical loads. So, I will depict both of these things in the revised updated graph or picture. So, let us say it stretches by a distance u naught. So, first what I am doing is I am just stretching or pulling this line AD in the positive x direction by a distance u naught, and when I do that, then this is my new location. Okay. And now this is my mid plane, and then I rotate it, and then I rotate it. So, when I rotate it, the new configuration looks like this. Okay. So, this distance is u naught, and this rotation is by a certain distance. So, we will again mark these points here. So, the revised positions are A prime, this is D prime, the mid plane is there. So, this is B prime, and a distance below that is C prime, and the overall configuration looks something like this. Okay. So, three things have happened actually. Three things have happened, not just two things. Three things have happened. I have pulled the plate in u direction, in x direction, I have rotated it, and I have also pushed it downwards. Otherwise, this B prime would lie on the original mid plane line, but now it has gone down. Okay. So, how much I have pushed it down? The mid plane has gone down by a distance w naught. So, this is w naught. Okay. And the rotation has happened by an angle, let us call this angle alpha, and the distance B to C is still z, and it does not change because we have said that the line AD, it does not stretch or contract in the z direction. So, B to C also does not change. Okay. So, B to C distance still remains z, the line has, the midpoint has shifted down by w naught, it has gone out by u naught, and line AD prime has rotated by an angle alpha, and the new mid plane line is this thing, and this angle is still 90 degrees, because we assumed that earlier that there is no shear happening, and when there is no shear happening, then this angle remains at 90 degrees. Okay. So, we will write down couple of important points. Point B prime, it moves by u naught in x direction. So, we are talking about the midpoint right now, we are just talking about the midpoint of the system. Point B prime moves by distance w naught, w naught in the positive z direction, in z direction, and AB, this line AB, it rotates by angle alpha. Okay. And it is rotating because the plate is bending, so it will rotate. So, then the question is, what are the coordinates for point C? This is the question. We want to calculate the coordinates of point C, or actually I will not call it, what are the displacements for point C, not coordinates, because what we are really interested is in displacements. And point C is any point lying on line AB, and it is z millimeters or meters off from the midpoint, midplane. Okay. So, we want to figure that out. So, displacement of point C in x direction is equal to what? See, it is equal to this distance. So, what is the displacement of point C? First thing is point B moves out by u naught, and with respect to the new position of B, C is moving inwards by some distance, this distance. And what is this distance? This is nothing but z times alpha, because this angle alpha is extremely small. So, if you compute, it will be actually z times sine of alpha, and sine of alpha is same as alpha. So, it works out to z times alpha. So, the total displacement of point C is u naught minus z or times alpha. Now, this is the situation when the plate is, so suppose this is my x direction. So, this is my displacement in this direction, I call it u. So, when the plate bends like this, and if there is a point C on this vertical edge, then its motion will be u naught, which is the midplane displacement, minus z, which is the coordinate of that point, times rotation alpha, and that is when the plate rotates, bends like this. Okay. Now, the plate there can also bend like this in the y direction, because when I am putting load, it will bend like this, and it will also bend like this, it will also bend like this. So, point C will experience not only displacement in x direction, but will also experience displacement in y direction, and we can create a similar figure, and we can, using similar figure, but for the y direction, we can say that displacement of point C in y direction is equal to u naught minus z times. Now, in that direction, let us say the rotation of that vertical line AB is beta, then I can call it z times beta, whatever is the angle in the other plane, rotation in the other plane. Okay. Next thing we know is that alpha is equal to del w over del x. So, it is v naught minus z times beta. Okay. So, alpha is del w over del x, right. Basically, it is the slope of this line, and slope of this line is del w over del x. And similarly, we can say that beta equals del w over del y. Okay. So, this displacement is, so we can say displacement of C in x, what is it? It is u, it is not u naught, and u changes from, it can vary from point to point. So, it is u is a function of x, y, and it also depends on z, because z is here. Okay. So, u x y z is equal to u naught, and what is u naught? U naught is the displacement of point B, and point B always lies on the midplane. So, when it is lying on the midplane, z is immaterial. So, u naught only changes from point to point. So, u naught is a function of x and y minus z times del w naught x y divided by del x. Okay. Similarly, displacement of c in y direction is v, and it changes from point to point, and it also depends on z, and this is equal to v naught, which is the midplane displacement at that coordinate system x y, but it does not depend on z because it is already at midplane. So, del z is already prescribed minus z del w x y over del y. Okay. So, this concludes our discussion for today. What we will do is we will use these relations to develop now more formal strain displacement relations for composite laminates, and that will form one important basis over which we will develop a more detailed theory. Thank you, and we will meet tomorrow with the same topic. Thanks a lot.